Hi everyone. I want to first thank the organizers for the opportunity to be here and for setting up such a nice conference. It's been really fun. So I'm Daniel. I'm going to tell about this work that I did in collaboration with Michał Osmaniak in Poland on classical simulation of linear optics under the effect of losses. Okay. So let me start by giving you kind of the general motivation that led us to this question. And it fits in this context of this. Okay. Better? So it fits in this context of this quantum computational supremacy or quantum computational advantage that Jens mentioned on Monday. And the idea is the following. So building a quantum computer is hard, right? So, you know, if you want to do Shor's algorithm, the error correction, the overheads are pretty nasty. And so recently, people have been looking into these intermediate models, which could provide some sort of medium-term alternative to building an actual universal quantum computer, okay? And some examples include, for instance, random quantum circuits, the stuff that Google's doing, circuits of commuting gates, and Boson sampling, which is the one that I'm going to talk about. Okay? So what are the disadvantages of considering these kind of intermediate models of computation? Well, first, they typically don't have error correction. Many of them don't have any practical application, so the only practical application would be just prove that quantum computers can do something stronger than classical computers. And as Jens mentioned a lot on Monday, it's often hard to check whether the device is working properly. Okay? On the other hand, you know, these typically require simpler resources, right? So both in resource count and the nature of the resource than building a universal quantum computer. And the thing that interests me the most is that it could bring new insights to quantum computing, and in the case of boson sampling specific, to quantum optics. So this is going to be the outline of my talk. I'm going to give some very basic introduction to boson sampling, tell you about how we model losses in linear optics, and what are the previous results that were known before this work, and then tell a little bit about our work in these three different ways of modeling losses in linear optics. So first, very basic boson sampling introduction. Boson sampling, you can think of it as the following physical system, right? So you start off with some m photonic modes, n of which are each populated with a single photon at the end. These pass through some network, some interferometer, which could be some like network of beam splitters and phase shifters. They come out on the other end, and you measure. You put photon counting detectors at the end, okay? And you do this many, many times, and you accumulate statistics, right? So the object we're interested in is this probability distribution at the end, overall possible outcomes, all right? And even though I'm thinking of this in terms of boson sampling, this actually, you know, this sort of outline actually describes different types of linear optical experiments. So the results themselves are going to be more general than just boson sampling. And the computational task of boson sampling is to sample from this distribution, okay? So to produce a single sample from the distribution that is predicted by quantum mechanics. Now, for a quantum device, this is easy. And you notice the scare quotes around easy. I am a theorist, not an experimentalist, and I don't want them to hate me. So, you know, it's not actually easy. We know all the technological challenges of doing this kind of experiment. But it's easy in the sense that you're just observing photons behaving in the natural habitat, right? So just watching photons being bosons, okay? On the other hand, there is good evidence that it would be very hard for a classical computer to simulate, to sample from this distribution. And the underlying reason is that the probability, the transition probabilities here are given by this permanent function, which is a matrix function that is very, very hard to compute, okay? And the fact that the probabilities are given by these permanents suggests that a reasonable milestone would be to perform an experiment of this type with roughly 50 or 100 photons, because then you would already be doing something that even a supercomputer can't really simulate, a classical supercomputer, okay? So, you know, this was proposed by Aronson and Arkhipov in 2012, and then soon after, the first experiments were done, and in the groups in Rome, Brisbane, Oxford, and Vienna. And all of them had a kind of similar outline. You have some photon source, maybe parametric down conversion. You pass your photons through some integrated photonic device, like we heard about on Wednesday, and you feed this into the detectors, okay? So this is just a sort of physical instantiation of that abstract physical system that I described before. And so these first experiments were done with 3 photons. And I think that the current record, is 8 photon experiments by the groups in China. But soon after these first experiments were done, people started asking, okay, but how is this going to scale up, right? So we don't have error correction. And here you have many, many problems that arrive from like real-world effects, like, using probabilistic sources. You may have some fabrication errors, mode mismatch, losses, dark counts. And what I'm going to focus on now is just losses. Okay, so how do we deal with the problem of losses? So just to tell you what was known previously before our result. So I had this previous paper with Scott Aronson where we showed that if you have boson sampling and you prepare n photons, okay, and you lose k of them for some constant k, the computational power of boson sampling doesn't change, right? This remains as powerful as kind of standard boson sampling. Now, this is very unrealistic because it's losing just a constant number of photons in the asymptotic limit means that the loss probability per photon goes as 1 over n, which would mean, the more photons you prepare, you want each one of them to be less likely to be lost, right? And that's very unreasonable, but, it's a step in the right direction. And our result also holds for when you have dark counts. And we also assume that the losses happen either at the input or at the output of the circuit, and this is going to be important. Now, so, this is coming from the side on just a little bit of loss, but you can also prove that if there's too much loss, then this computational power vanishes. So there was this paper by Rahimi Keshari, Carl Caves, and Tim Ralph, where they showed that if you have more than 50% loss and 30% dark count probability, boson sampling becomes classically simulatable via positive Wigner functions, basically. Positive Wigner function, so you can describe the entire thing as kind of a classical probabilistic process. So, pictorially, what this means is that, if you were to plot like loss probability per dark counts, we know that there's kind of this tiny corner here where everything's still okay. We know that, there's this faraway corner where things get really, really bad and you don't have any computational power anymore. So the result that I'm going to tell you about today is the following. So we give an efficient simulation, efficient classical simulation of boson sampling if only order square root of n photons are left. Right, so you prepare n photons, and only square root of n make it to the end of the experiment. All right? If that happens, then you have an efficient classical simulation. Okay? So this means that we've pretty much closed off another chunk of this region here where you can't get any computational advantage with boson sampling. Now, you could also think that this may be a little bit too extreme. If you've prepared n photons and you only have square root of n of them at the end, you've lost most of them, right? But by the end, I will argue that this is, not that unrealistic. No, exponential, I mean exponential, 1 minus exponential, right? So 1 minus something that approaches exponentially 1, or zeros, right? So, if you're talking about loss probability, it just decreases, then the survival probability decreases exponentially. That's what I mean. Yeah. So now let me tell you what our results are. So we're going to consider 3 different ways of modeling losses in linear optics. But before I tell you about these 3 models, I want to talk a little bit about how we're going to kind of mathematically describe these systems. And just sort of repeat what I said before. This boson sampling setup, you have m modes, and you have n single photons at the input, and you had some circuit of beam splitters. Okay? Now, and this is linear optics because it acts linearly at the level of the creation operators. Okay? Now, imagine that you want to map this to a quantum circuit, right? So you want to simulate this thing with a quantum computer. And why would you do that? Well, what I'm going to argue later is that we're going to map this to a quantum circuit and then use well-known results from classical simulation of quantum circuits to prove that you can classically simulate this guy as well. So there are 2 ways that you could map this to a quantum circuit. One of them is based on this, what we've called second quantization mapping, right? And here, you have the circuit, and you're going to map each mode to a qubit, right? And the qubit here is going to tell you how many photons are in that mode, right? So this qubit has to be an n-level system, because you can have up to n photons in a given mode. And when you do this mapping, every 2-mode transformation here, a beam splitter, gets mapped to a 2-qubit transformation here, okay? And the reason why you would consider this sort of mapping is because it preserves the geometry of the original circuit. So if you're asking, for instance, about the computational power of linear optics with, say, small depth circuits, the depth is something that's going to be preserved when you map from this guy to this guy. Okay? But here we're going to use a different mapping, which is going to be the first quantized mapping. Right? Here, you're going to map, rather than mapping each mode to a qubit, you're going to map each photon to a qubit. Right? So now you have n qubits. And each qubit is going to tell you in which mode that photon is in, right? So now they need to be m-level systems, okay? Now we know from quantum mechanics that if you have a bunch of particles and they're bosons, they have to be in the symmetrized state. So when you map this to the quantum circuit, you're going to have a procedure here for creating the symmetric state over all these guys, right? But if you do that, then all the linear optics, right? So this entire linear optical circuit here just corresponds to a tensor product of single qubit gates here, right? And this is going to be important. And the reason why you do this is because it's easier to think about properties of the input state. So things like photon loss or partial distinguishability of the photons, okay? So for instance, if some subset of your photons are distinguishable from the rest because they have some internal degree of freedom like polarization that is different from the others, they would be mapped in this description to just something that does not go through the symmetrization procedure, right? And in particular, if all your photons were distinguishable, this would just be a tensor product of single qubit states, okay? So in some sense, you know, in this picture, the computational power of boson sampling is coming from the entanglement that is generated by the symmetrization procedure, right? If all your photons are distinguishable, this is classically simulatable, right? Because now you just have to simulate the dynamics of these states that are all separate and that are subject to this kind of tensor product dynamics. And so this is clearly classically simulatable, and so in some sense the computational hardness of boson sampling has to come from this entanglement that's generated by the symmetrization, right? And this is going to be important, you know, so we can define these product bosonic states, which are just states of this form, where there's none of this entanglement, and separable bosonic states just by the natural extension to mixed states. And this is going to be important because our simulation is going to be of this type, right? So we're going to simulate lossy boson sampling via distinguishable particles, right? So via these product states. Now, so let me tell you what's the first way that we consider how to model losses. And this model is going to be the fixed loss model, right? So the idea here is that you've prepared n photons and you've lost a well-defined number of them. So you lost exactly n minus L of them and you only have L left, okay? And in this description, the way that you model that is just by tracing over some, you know, subset of the particles. Trace over n minus L of them, okay? And this state that comes out here is the state that we want to simulate. And one nice feature you can convince yourselves easily is that if you do this, then losses commute with linear optics. So you can assume that all losses happen at the input of the circuit, right? So we only actually care to simulate the state at this stage. So, okay. And okay, so then now our central question that, you know, is behind all our results is the following. So if L is small, so if there's just a few number of photons left, does this state become separable, right? Because we have this entangled state here, and you're going to trace over a bunch of particles, and we know that this is going to degrade the entanglement on the remaining particles, right? So the question is, does it ever become exactly separable? And the answer is no, it doesn't, except in the trivial case where only one photon's left, but then it doesn't, and in fact, if it did become exactly separable, it would be a bit too strong. We would have a result that was a little bit too strong. But then, you know, this is not even the right question to ask, right? So we don't want this state to become necessarily exactly separable, just close to being described by a separable state. So then the more general question that we ask is, okay, given that this state rho L, which we want to simulate, is not separable, how close is it to one that is separable? Okay? And as our figure of merit, we're going to consider the trace distance between the two states. And the reason why we do this is that by a property of the trace distance, you can show that if the trace distance is smaller than some delta L between these two states, right, so the lossy state and the state we're going to use to simulate it, then it does not matter what linear optical transformation you apply or what measurements you make, the distance is also going to be smaller than delta L in the total variation distance at the level of the output distributions, okay? Which is the distance that you care about for probability distributions. Okay? So it's going to be sufficient to describe to find one state that is close enough to the state that we care about at this stage. And so I'm just going to state our main result. We managed to prove that this distance, delta L, between the state that we care about and the closest separable state is given by this ugly thing here. Now, this is not, don't worry about this too much, not very interesting. But you can prove from this that if the number of photons that are left grows more slowly than square root of n, then this delta L becomes approximately L squared. This delta L becomes approximately L squared over 2n. But now if L is smaller than square root of n, this tends to 0 as n increases. Okay? So this shows that this state sigma, which I have not described yet, gets closer and closer to the state that we care about as the number of photon increases. Sorry? Oh yes, so this is an exclamation mark, and these are factorial, yes. No, yeah, okay. So basically, this is the main punchline, right? Is that if less than square root of n photons are left, then the quality of the simulation, which I have not described yet, improves with n. Okay? And then you'd expect that any computational power of boson sampling disappears. So the state sigma that minimizes this trace distance is the following. So it's the separable state, and what you do is you start with L of these qubits, and you apply these Fourier transforms, so you just create a equal superposition of all basis states. And then you apply this guy here, which is just a diagonal gate with random phases, right? So you choose a set of random phases, and this is just going to be the phases on the diagonal. But they have to be the same one for all the qubits, right? So the point is that the output probability distribution that you're going to get from this simulation is close, in the sense that I mentioned previously, to what you would get from the lossy boson sampling experiment. Okay. Now, this was for this first model of fixed losses, but that's not the way that we usually model losses in optics. So here we now consider this uniform beam splitter losses. So what I mean by beam splitter losses are the following. So you have some loss element eta, right? And then this means that the photon passes through here, it tosses a coin. With some probability eta, it goes on ahead. With some probability 1 minus eta, it gets lost, right? And this can be modeled by just this kind of adding an extra beam splitter that can reflect your photon into some modes that you're not going to measure, right? So you're just going to lose. And this is the way that we usually describe losses in optics. And if you do it like this, if you consider this model, it has first a very useful property that uniform losses commute with linear optics, right? So if you're doing some interferometer where you have the same amount of losses on all modes at a given stage, you can always pull these guys to the input of the circuit. Okay? And if you model it like this, essentially what you have is just a binomial distribution over the states that I was describing previously, right? So each photon is going to toss a coin, and it might get lost or it might survive. So you're just going to give a binomial distribution over these states with a fixed number of photons, right? And so we are now asked, what is the closest separable state to this guy? And the answer is just, in the same way that this is a binomial distribution over these guys, this closest separable state is just going to be a binomial distribution over the separable states that we were describing before, that we're using to simulate before. Okay? And we use some properties of the binomial distribution, the fact that it's well concentrated at its averages, to show that our classical simulation is also efficient if you now use this state. And basically, this punchline is the same as before, that if the average number of photons that is left goes like square root of n, then this distance tends to 0 as n increases. Okay, so we have sort of the same punchline as before. Now, the third loss model that we consider we're going to call non-uniform losses, right? So in the previous two models, we could assume that the loss always occurred at the input, right? And this is a very common assumption in the literature. All previous papers on boson sampling consider this as well. But now imagine that you have a kind of linear optical network that's not balanced, right? So it's not very symmetric. And now the losses might depend on the path that the photon takes through the circuit. Okay? And so what we're going to assume here is that every time you have a beam splitter, you have two of these loss elements at the input, and all of them are equal, right? So any non-uniformity is going to come from just the geometry of the network rather than from these guys being different. Okay? But we do not assume that we are restricted to nearest neighbor beam splitters, right? So all my interferometers are going to be drawn with nearest neighbors beam splitters just because it's easier to draw like that. So basically, our result here then is the following. So let S be the shortest path between some input mode and some output mode, right? And I mean shortest in terms of the number of beam splitters that the photon has to go through, okay? So if S is the shortest path, then we prove that you can pull out S layers of uniform losses, right? So you can assume that there are S layers of these losses at the input of the circuit, right? And so this is a very nice result. I'm very proud of it, but I don't have time to go through all the details. And it's also very annoying because every example that we came up with, it was trivial and obvious why this result would hold, but it took a while, and we have to throw some graph theory at it to prove that it's always true. Okay, so basically what we do is we use this guy as a basic building block, right? So we know that these kind of, if you have equal loss elements, they commute through a beam splitter, right? Then using this as a basic building block, we take some ugly, very unbalanced interferometer, and we apply this identity over and over and over and over until we've managed to pull out some amount of losses to the input, okay? So, for instance, here, the shortest path has length 3, right? The photon has to go through these 3 beam splitters to get to the output, right? So this means that we can pull 3 rounds of losses to the beginning of the circuit. So we've managed, what we've shown is that this circuit is equivalent to this circuit, right? Now, the intermediate step is the thing that I'm going to gloss over, but basically you can find another, and it's interesting because it's constructive, right? So I can give you an efficient description of a different interferometer, which is mathematically equivalent to the one that you care about, where you've pulled out some number of layers of uniform losses, in this case 3, and you're left with an efficient description of what's left, right? And I think this has kind of general independent interest regardless of this Boson sampling stuff. So a consequence of this for Boson sampling specifically is that if the smallest path has length s, right, then this corresponds to having some effective loss here at the input, which scales exponentially with s, right? So the survival probability at each of these loss elements is eta, then the sort of overall survival probability per photon is going to be eta to the s, right? And in particular, this shows that that regime where I was mentioning before, where we only have square root of n photons left on average, that is already reached for boson sampling if you have some depth that grows at some c log n for some suitable constant c, all right? So this shows that you need to be below some c log n in order to avoid this classical simulation regime. So that's what I wanted to say. Basically, we've discussed how linear optical circuits are heavily affected by losses. For boson sampling specifically, this classical simulation is possible if you only have like square root of n photons left. And this is already reached for some log n depth of the circuit. And it's interesting that you can show that if your interferometers have this 2D architecture where every beam splitter only interacts nearest neighboring modes, log n layers are necessary, right? So you can prove that if you have less than log n layers, you also have a classical simulation via tensor networks. Okay, so what this shows is that if we can't manage to go to some 3D architecture when you have beam splitters between distant modes, formally there's going to be a very narrow window where you can still get some computational advantage with boson sampling. And this last thing that I mentioned, where you can extract the losses from the unbalanced circuit, I think it's also of independent interest, and in particular it strengthens all the previous results on lossy linear optics by proving on formal grounds when you can make these assumptions, right? Under what conditions you can assume that the losses happen at the input, which is what people usually assume. So there are many, many open questions which I find interesting. The main ones are, first, where does this complexity transition happen, right? So for how much loss does boson sampling actually go from hard to simulate to easy to simulate? The also, which I think is the most important open question for boson sampling, is can you get a computational advantage with log depth boson sampling? And this needs, it's a challenge for both theory because we have to prove whether that's true, And also for experiments, because then you would need to build these 3D circuits, right? You cannot be restricted to nearest neighbor beam splitters.
Thanks. Questions, all right?